in listen-only mode.
Good morning and welcome to Geospatial Survey and Mapping webinar on LiDAR Isn't Enough, Mobile Mapping with 3D Laser Triangulation. My name is Sonal Bahugna and I am Executive Editor of Geospatial Survey and Mapping and will be coordinator of this webinar. Geospatial Survey and Mapping has been regularly publishing e-magazine covering geospatial technology and their application. It publishes news articles, interviews, podcasts, and tenders. Today we have Richard Fox-Ivy, Principal Consultant, Pavemetrics. Richard Fox-Ivy brings a diverse background to the table. Richard's education includes majoring in philosophy with a focus on logic and argumentation, as well as training in the field of non-destructive examination. In the business world, Richard has launched his own cybersecurity startup and has run a successful Kickstarter campaign. Richard also has more than 15 years of experience in transportation infrastructure management field and has traveled throughout the US, Canada, Europe, and Asia helping asset owners to adopt and deploy technology for the better management of their assets. Participants are requested to put their question in the question box. The question will be taken after the webinar. Thank you, Richard, for joining us today. Over to you, Richard.
Okay, thank you, Sonal. I appreciate the introduction. I'm just going to do a mic check. Sonal, can you hear me properly?
Yes, I can.
Okay, that's great. Morning, everyone, or good evening if you're joining from somewhere over in North America, as I am. I wanted to thank everyone for joining me this morning for this session. I think lots of interesting things to cover. So let's jump right into it. So the title of the presentation is When LiDAR Isn't Enough, and we're going to focus on a technology called 3D laser triangulation. So first off, I want to put out there LiDAR is a great technology, and this presentation is not about whether LiDAR is a better technology than laser triangulation or laser triangulation is better than LiDAR. I truly believe that you have to pick the right tool for the right task. And LiDAR is great for a lot of applications. Some applications it's not ideally suited to. And really the topic of this presentation is to give you another tool in your toolbox so you can select the appropriate tool for the job at hand. And I'm sure that there are lots of people on this call that are very well familiar with LiDAR, probably not so many people that are as familiar with a technology called 3D laser triangulation. Okay. So I'm going to advance to the agenda. Sonal, can you just confirm that the agenda's come up on your end?
Yes, it has.
Okay. Okay, great. So we're going to start off with a bit of a talk about sensitivity, accuracy, the importance of millimeters. I'm going to focus on laser triangulation as a technology and explain how that works. I'm going to compare and contrast it to LiDAR so that everyone has a frame of reference. And we're going to talk a little bit about data processing and how that might differ from LiDAR. And then last but not least, we'll talk about spatially mapping the data and correcting it for geometry. First, however, very brief introduction. I work for Pavemetrics. Pavemetrics is a private company, but we're a spin-off of Canada's National Optics Institute, which is known as INO, and based in Quebec, which is a French part of Canada. And as a company, all we focus on is sensor development and algorithm development for the inspection of infrastructure. We're not in the business of collecting data, we're in the business of developing the technology for data collection. And our technology is used all around the world, 40+ countries to scan things such as roads, runways, railways, tunnels, including in India. And if you look at the global market, we've sold more than 400 systems all around the world. In North America, in the United States specifically, 40 out of the 50 state departments of transportation rely on our technology to scan their roadways every year for pavement condition data. So everything from what cracks are on the road to how rough the road is to ruts that are in the road, potholes, texture of the road, all those types of things are measured using our technology. And these are images of various different vehicles that are fitted with our sensors for that purpose. Okay, enough of an introduction. Let's talk about accuracy and the importance of accuracy. Okay, so Sonar, are we on slide 8 on your side?
Yes, it's running
Great.
absolutely fine.
Perfect. So let's say you're designing a road, and you're going to build a road that's about 1 mile long, which is 5,280 feet, and it's going to be 2 lanes wide for a total width of asphalt of 28 feet. And you're going to put down 3 inches of asphalt, which for us from the metric world is 76 millimeters roughly. And if asphalt costs you $75 a ton, which is a fairly current price in the US right now, you're going to need 2,772 tons, and it's going to cost you about $208,000. Okay? Now, if you go and you build that road, and you build it 1 mile long, just like the design says, and you make it 2 lanes wide, just like the design says, and it's 28 feet wide worth of asphalt, but you put down just 4 more millimeters, and asphalt's still $75 a ton, instead of requiring 2,772 tons, you now need 2,917 tons. You need 145 more tons of asphalt, and your costs have increased by $11,000. That's just 4 millimeters of asphalt on 1 mile, and let's face it, 4 millimeters is a very small amount. And if you look at the accuracy per point of a technology like LiDAR, for example, plus or minus 5 millimeters is kind of where it tops out, okay? So put too much down can be very costly. So if you don't get the measurement right on that side, that's an issue. If you don't get the measurement right on the other side, if you build a concrete road, for example, and you're under thickness by just 10%, you can actually reduce the life cycle of that same road by 90%. So accuracy is important, and it depends on what you're measuring, it depends on the application, but when you're doing things like inspecting roads or inspecting rails or inspecting tunnels, the tolerances are really tight, and LiDAR in those cases is not necessarily going to be your best tool. So here's a few examples of places you might want to think about other technologies like 3D laser triangulation. So if you want to detect cracks in pavement, okay, most roadway agencies are looking at cracks that are in the range of 2 millimeters wide and a few millimeters long. You can't measure those kinds of things with something like LiDAR. Railroad assets, if you're inspecting the rails themselves or the ties themselves, LiDAR is a great technology for seeing sort of all the assets and how they're all related, but getting into the details of what's the actual condition of those specific assets, it's maybe not quite accurate enough, not quite enough resolution either. And then doing things like digital train modeling, inspecting tunnel walls, all these things. So if millimeters are important in what you're doing, then I suggest you might want to think about 3D laser triangulation. So let's talk about what 3D laser triangulation is. How does it work? And I'm going to start off with compare contrast with LiDAR because it's a nice frame of reference for a lot of people. So LiDAR is a time-of-flight technology typically. Okay, we send a pulse of light out and we measure how long it takes in time to go to an object and to come back. And because we know the speed of light, we can then translate those times into distances. Generates something like 200 to 400,000 points per second. Vertical accuracy point is per point is usually plus or minus 5 millimeters, something in that range, if you're doing things well. It's a great technology when you've got a large surface you want to scan or a large area. Okay, I always think of things like a farmer's field or an intersection where I want to see where the lanes are and the signage, or maybe the side of the building, big objects. It's also great over long distances. You know, you can be a few kilometers away, you can hang it off of a helicopter or hang it off of a plane, and you can get data. So it's really nice that way. And the way LiDAR systems are designed, there's moving parts, so you can set down a tripod and the LiDAR is still going to scan the area around it. You don't have to move the LiDAR sensor to get a scan. Okay? But of course, we all know there are also mobile LiDAR systems out there. You can mount a LiDAR system in a truck and drive it down the road. Let's compare it to laser triangulation. So laser triangulation, it's not time of flight. We're not timing how long it takes to send a pulse of light out and then come back. We're actually solving a triangle. We're using trig. And the triangle is formed by, if you look at these sensors, there's a rectangular window on the bottom. That's where a laser is emitted. And there's a circular window at the top. That's where the laser light is received. That's the base of the triangle. Okay, so this sensor, imagine it pointing down at a road or at a railway. So the base of the triangle is on the sensor. And then wherever the laser line is projected onto, so the road, let's say, or a tunnel wall, that's the top of the triangle. Laser triangulation is really not suited to big surfaces. You're not going to set one of these sensors up and scan an intersection. It really doesn't work that way. It's much better suited to a smaller surface where you need really high resolution and really high accuracy. So instead of 200 to 400,000 points per second, you're talking more like 100 times that, 45 million points a second. And instead of plus or minus 5 millimeters, you're talking about plus or minus 0.1 of a millimeter. Okay? It's also limited in terms of range. So you set up the focal length of these systems, and you're going to need to be a few meters away from the thing that you're scanning. So you're scanning a road, you're going to mount the sensors on the back of a truck that's going to drive down the road. Scanning a tunnel, you're going to mount the sensors on a frame that's going to drive. It's going to be attached to the vehicle that's going to drive through the tunnel, that kind of thing. And then last but not least, a little different than LiDAR, there's no moving parts here. Okay, so there's nothing to wear out, which is nice, but as well, you need to actually mount them on a vehicle and move them past the thing that you want to scan. It's the motion of the vehicle that allows the sensor to scan the surface. So, Sonal, quick check. Are we on slide 13? Can you see the diagram there?
Yes, I can.
Great. Okay. So here's the triangle that I mentioned to you before, and I hope that seeing this now will sort of fix it in your head. So you had the rectangular window, which is where the laser line was being projected. You had the camera, which was the round window where the light was being received. And then you have the top of the triangle, which is on the surface that's being scanned, the road or the runway or the tunnel or the rail. And how does it work? How do we solve the triangle? Well, we know the distance between the line laser and the camera. Okay, we know the angle with which that line laser is installed and the reference towards the surface. So we know the angle with which it's projected. We can measure where the light is received in the camera sensor, so we know that position. From that position, we can then determine the angle with which the light was received, and then ultimately we have enough to solve for X, which is the surface that we're trying to recreate through laser triangulation. Two types of data come out of the system. Shouldn't be too surprising for someone who's used to seeing LiDAR. You have range data. In this case, this is a grayscale image that's been prepared, and the darker the color, the farther away the surface. The lighter the color, the closer the surface is to the sensor. So you're looking at a road here. The black lines are cracks in the road. Okay. You have to think of this as like a slice out of the 3D data. Really, there's a very detailed wireframe model here, but we're just taking a slice at a particular height of interest, a range of interest. In this case, the range is focused on things like cracks. Then the image on the right, which is captured simultaneously, is actually a picture of the surface. Okay, we're measuring the intensity of the laser light that's received back to the camera, and we've got a picture. And what's neat about this example is that it shows you the value of having that range data, because if you had to pick the picture that it's easier to find the cracks in, you'd pick the one on the left. You'd pick the range data. It's painfully obvious where they are. The cracks are visible in that intensity image on the right. If you zoom in, you'll see them. It's a really nice image, but this just illustrates how valuable having the right tool for the job can be. And if I hit the button here, it's going to merge these two images, and we'll have a 3D representation. And then the last piece of the puzzle that moved it over top is the results of automated data processing. So there's an algorithm here that's gone through and processed the range data, and it's found all of the cracks that are at least 2 millimeters wide and about 3 millimeters, 4 millimeters long. And it's recorded their location, where do they stop, where do they start, the width, the depth, all of the relevant information. Here's another example in a railway environment. I've kind of flipped them around. You've got intensity on the left this time, range on the right. So you can see same kind of idea here. Okay, slide 16. Bunch of piece of information about the sensors here. I'm not going to talk about each one of them. There's a few that I've highlighted in red that I did want to point out. One of the nice things about this technology is it can be used anywhere from 0 to 160 kilometers an hour. Frankly, you can use it faster in applications like railway, but that's kind of a normal scanning range. As I mentioned before, it captures not only range data, but also full intensity image, a JPEG image of the surface. It can be used day or night. And really one of the big advantages of this type of technology is that from a processing standpoint, you don't get point clouds. Bundled with this type of technology comes algorithms to automatically detect features that you might want to detect and make measurements you might want to make. So that's a big difference. And we'll look into that. We'll go into that in further detail. Another one of the differences compared to something like LiDAR is that in most cases LiDAR, when you're collecting data, you've got a scanning frequency, and you're basically just free running. And so if you're using mobile LiDAR on the road and you slow down, you come to a stop at an intersection, that LiDAR scanner gets a huge amount of points in the area that you stopped in. It's rescanning and rescanning and rescanning. Laser triangulation a little bit different. We use pulses from an optical encoder, which is mounted on one of the driving wheels, that turns the wheel's revolutions into linear distance down the road, or down the tunnel, or railway, what have you. We use the pulses from that optical encoder to capture data on a distance basis. So when the vehicle stops, we're not capturing data. When the vehicle starts moving, we start capturing data. And you can trigger as frequently as a scan every millimeter of travel along the road or along the rail or whatever surface. So incredibly high resolution, every millimeter scan. And then transversely, there's a point every millimeter as well. Okay? So it's a millimeter in the X, it's a millimeter in the Y, and then in the Z, you can go all the way up to 1/10 of a millimeter in terms of resolution. Here's a kind of a typical mounting setup. So as a sensor manufacturer, we don't build vehicles like this. We just supply the sensors. Then other people, our customers, they'll take the sensors, they'll build mounts, and they'll install them on vehicles. The DMI that's referenced in the top image there, that's distance measurement instrument, which is another way of saying an optical encoder. And you can see at the rear of the vehicle, the sensors there, they're mounted above the pavement. It's about 2.2 meters off the pavement surface from the bottom of the sensor. In the rear of the vehicle, you have a sensor controller. You have a power inverter, which takes direct currents from the vehicle's alternator and creates alternating current for the sensor controller, and then the sensor controller actually supplies different voltages that the sensors require. And all of the data is stored on an industrial PC. So typically you have, removable hard drives that might be 1 terabyte or more in size, and as the vehicle's rolling down the road, it's filling up hard drives. And then at the front of the vehicle, you can have an operator station, usually kind of a laptop that's networked in, and pretty straightforward. System doesn't require a lot of monitoring as you're collecting data. It just kind of runs automatically. So you hit start and you start driving, and it'll flag you if there are issues as you're collecting. So here's another example to kind of put these two pieces of the puzzle together. So I said before that there's no moving parts in here to scan the area. So how do you get a scan? So the illustration on the left is our sensor with the line laser and the camera, and this time I've put in some lenses there. And so as the vehicle is moving down the railroad track, that line laser, where it's intercepting, is changing. And so you can kind of imagine there's this line that's scanning the full width of the railroad track, the ties and the ballast, and so on and so forth, as the truck moves down the track. So here's kind of a nice example of taking that range data and the intensity data and putting them together. So we've draped the intensity data over top of the range, and this kind of result is automatic. There isn't a bunch of complicated processing that has to be done. You're not clicking on points and registering anything. This is the native file that comes out of the system. We've opened it in a 3D viewer, in our 3D viewer, and this is what you get. And you can float this image around and look at it from all kinds of different angles. Next slide is showing you that 3D wireframe model that I mentioned before. So before we kind of looked at range data as a grayscale image, which is just a slice out of this wireframe model. But if you look at this picture, you can see all of the little individual triangulated points. And again, this is just natively out of the system. There's no specialized processing to produce this. And the next image is the intensity image of the exact same point that was captured simultaneously with the same sensor. Okay, so let me give you a few sample images and compare them to LiDAR, and just to kind of illustrate again kind of pros and cons of using LiDAR, pros and cons of using laser triangulation. So first example is a railroad. Nice LiDAR scan. What I like about this image is that I can see the sleepers of the ties. I can't quite see the rail, but I know that the rail is there. And I can see a lot of the surrounding area. So if there were assets that were encroaching around the railway track that were maybe safety issues, I'd be able to see that. So it's nice from that perspective. But I can't really tell what condition the ties are. I don't have any sense. I've got a few points on those ties, but maybe I could see if there was one that was missing, but I can't tell much about them. And I can't tell where the fasteners are. Are there missing fasteners? Are there damaged fasteners? Whereas this next image from the paid metric system, 3D laser triangulation, I can see there's a water bottle here. I can see the fasteners. I can read the signage. I can see the ballast. I can see the sleepers. I can see the rails. And I can make measurements of all of those features down to millimeter by millimeter. So if I want to inspect all these assets, laser triangulation is going to win this round. If I want to see what else is going on around the railroad track, then LiDAR is going to win the round. Here's a nice example of a LiDAR scan of an intersection. Same kind of idea. What I like about this is that I see the lanes. I can see there's a railroad crossing. I can see signage. I've got a really good sense of what's going on around me. But if someone said, can you find the cracks in this road? Can you rate the condition of this pavement? The answer is no, I can't. I don't know. I can't tell. This image I can tell from laser triangulation. So all of the cracks here have been automatically detected, and the parameters, the length and width and orientation has been recorded automatically. But I can't see what else is going on around me. So that's the difference. I'm focused in on one area and I have a lot of resolution. Okay, Sonal, just a quick check. Are we on slide 28 on your end?
Yes.
Great. Okay. So we talked a lot about how laser triangulation works in terms of what type of data you get out of it, what the measurement principle is. We've compared and contrast it to something like LiDAR, maybe some of the pros and cons. We haven't really talked a lot about positioning that data and orienting that data, and that's really important. It's important in the LiDAR world. It's important in laser triangulation as well. People want to know where the data is, and you need to make sure that when you collect the data that you compensate for the way in which it's collected. You compensate for vehicle motion so that when you get a scan of a surface, the shape of the scan isn't impacted by what the vehicle was doing at the time of scanning. So let's look at it this way. You're driving down a road, you've got things like vehicle acceleration, deceleration. You hit the gas or you've got a brake because someone's in front of you. You've got pitch, right? When you jam on the brakes, the vehicle pitches forward. If you're moving into a corner or you're swerving around something, the vehicle's rolling. You've got centripetal force, you've got gravity, a lot of factors that are impacting the vehicle. And all of this is impacting the data as well if you don't compensate for it. So how do we do that? Well, we use inertial measurement units, like many people in the LiDAR world are familiar with. We supply our own inertial measurement units. We actually mount one on each of the sensors, and we align it with the laser window. And those measure the pitch and the roll and the heading of each of the sensors. Sometimes we get the question, well, why two? Why do you have, why not just one? The reality is because we're scanning at such a high resolution, such a high accuracy, we need to know exactly what each one of those sensors is doing. We can't just take the pitch roll and heading changes of the vehicle and then correct the data. We're handling millimeters and fractions of a millimeter, so we need to have one on each of the sensors. This is our optical encoder that I mentioned before. So this is giving us linear distance down the road or down the track. And you can see it's just attached onto the studs or the lug nuts of the vehicle. And it's translating. Every time that wheel rotates, it generates 10,000 pulses. Okay? And those pulses are what we use to trigger the millimeter scans or the scans every 2 millimeters or 5 millimeters, whatever the interval the client is interested in using. Of course, we have GPS data that's coming in, so we've got latitude, longitude, elevation as well for the vehicle. So one of the challenges then is we have all these different coordinate systems, right? We've got IMU data, we've got linear data, we've got GPS data. So how do you get everything onto the same plane? How do you coordinate everything and consolidate everything? So one of the things we do is we have a calibration object. This is a precision machined object where we know all the dimensions, we know all the angles, and we set it down on the road or between the rails or wherever we're scanning, and we move the scanners over top of it. So we get a scan of the same object with each of the sensors simultaneously. And that allows us to calibrate those two sensors together. So we have an automated calibration process. You can see kind of a screen capture here showing you it's a 1, 2, 3, 4-step process. And you drive over top of the sensor and it kind of guides you through the process of making that calibration. So this image is showing us what the 3D points look like from that object as we drove over top of it, and it's two sensors that have been merged automatically. Okay. Next image is the intensity data for that calibration object as we've driven over top of it as well. And what we're looking for here is a really nice seamless kind of merging of the left and right sensors in the middle. So I'm looking at this pavement marking and I'm not seeing any seam. I'm looking at the calibration object. I'm not seeing any seam. I'm looking at the shape of the rocks in the road. I'm not seeing any seam. So this is a really well-calibrated pair of sensors. Why is all of this important? Because I talked a little bit about, hey, we've got all these motions happening. We've got all these forces acting on us, but how does it affect the data really? Here's a nice example. So this is a speed bump, and the vehicle would have started on the right-hand side of the screen and driven over top of the speed bump. And if you look at the left-hand side of this image, it kind of waves up and down. Okay, the road looks like it's going up and down, and you can kind of see there's this roll in the road. And if you didn't have any other data, you might just assume, hey, the road's kind of bumpy there. I mean, it looks bumpy. Reality is it's not. The reason why those bumps are there is because as the vehicle went over the speed bump, the sensors that are at the back of the vehicle, they got closer to the road, then further away, then closer, then further away, as the shocks, the suspension of the road reacted to all those forces. So if we have IMUs on board, inertial measurement units, and we measure the pitch and the roll and the heading and we correct the data, then we get an image like this. So if you look again at the edge of this pavement, now it's straight. And if I look at the area to the left of these speed bumps, it's smooth. There aren't rolls in the road there. It's not real. I'll just go back for a second to the prior picture. So again, you can see the waviness of the scans. So it's really important that you have IMUs on board and that you develop the right algorithms to be able to correct for these factors. Especially, again, let's go back to that first example of the road where we put down 4 millimeters too much. Let me tell you, there's way more than 4 millimeters here of difference between reality and what was measured. And let's face it, you're never going to pave just 1 mile at a time or build 1 mile at a time. It doesn't work that way. Here's another example. Here's a road profile without any geometric or dynamic corrections. And what I want to point out to you is a few things. Look at the pavement marking. There's some interesting sort of waves in it. Now there's some large transverse cracks in the road, okay? That's a bit of a hint. The other thing is the road is really straight, like very strangely straight. It's possible that the road is this straight, but I'll let you in on a little secret, it really is not that straight. So I'll show you what the road looks like with those corrections. And look at the pavement marking, nice and straight, nice and flat, even after going over that transverse crack, because the road is not wavy after that. It's just that the vehicle suspension was reacting to the crack. And we can see there's some vertical curvature here. We're going up a hill. There's some horizontal curvature. We're banking to the left. So now we've corrected the road for the actual conditions that are present, and we're measuring the actual road, not just the vehicle's response to the road. Here's a really nice example of rail. I showed this picture to someone who's responsible for rail inspection, and they said, "Oh my goodness, this is a horrible condition. The switch, where is this?" I said, it's not real. Don't worry. This is prior to doing any kind of geometric correction. Okay, so the vehicle drove over top of the switch, lots of rough area going through the switch, made the vehicle shake back and forth, and you got these really strange snake-like rails. This is what the switch actually looks like. Okay, nice and straight. We've restored it to how the actual rail looks in real life. So we've corrected for all of those vehicle motion issues. So from a data processing standpoint, let's talk a little bit about that. And this is one of the last segments of the presentation. One of the big differences is you're not dealing with point clouds. So when it comes to laser triangulation, we develop computer algorithms that automatically sift through millions and millions of points. And we can automatically detect differences of only a few millimeters. So from a labor standpoint, from a time to complete the project standpoint, from a repeatability standpoint, from an objectivity standpoint, number of advantages over something like LiDAR. Here's a screenshot of a processing application. This application will allow you to process single sections, let's say a 10-meter length or a 5-meter length, or it'll allow you to process 10,000 meters or 10,000 kilometers at a time if you wish. And it takes the 3D files from the laser triangulation sensor and it outputs JPEGs, so user-friendly format. You can give pictures of the rail that was inspected or pictures of the road, and it also gives XML data. So basically all of the measurements that were made or the defects that were detected. From a data processing standpoint, from an algorithm standpoint, we actually develop algorithms that look at not only the 3D shape of the surface for things like a crack, which would be a distortion to the 3D shape, or a rut in a road, but we also look at the intensity data. So how much light is reflected? Pavement markings, for example, have glass beads in them, and those glass beads reflect a lot of light. So we can develop an algorithm where we detect the pavement markings automatically. and then use that to generate break lines or use that to create a line inventory or some other application. And then we also look at the other streams of data like the geometric data from the IMUs, and that's how we correct the images for the vehicle motion. So here's a few illustrations of what those outputs look like. We've got graphical outputs of JPEG images. In this case, the colorization over top of it is saved as a separate layer, and those are the results of the automated data processing. So we've detected the lanes, we've detected all the cracks, we've detected the markings, we've detected edge drop-off, etc. And then up on the right-hand side, you've got the XML data, and on the bottom right, you've got a Bentley microstation file. And we can produce LAS files as well, although LAS, from our standpoint, is not a great format for this kind of data because we have so many points. The LAS files are enormous, and really we have better internal tools, better internal formats for handling the volume of data. But if you're familiar with LAS or you like that file format, that's available. Let me give you a few examples of what kinds of things can be done from a processing standpoint. So this algorithm goes through, takes for a 10-meter section a couple of seconds on a high-end computer to find all the cracks that are 2 millimeters and wider, and it rates them according to how wide they are. So it says what's the severity. Is it a low severity, moderate severity, high severity? It classifies it. Is it a transverse crack? Is it a fatigue crack? Is it a longitudinal crack? So these are all things that are relevant for a road agency that is trying to better manage their pavements. They want to know how severe are the cracks and what kinds are they. And that tells them something about maybe how the cracks were formed and what's a good treatment for the crack. Here's a nice railroad example. So railroads want to know things like, am I missing fasteners? Or am I missing spikes in wooden ties, right? Once you lose a certain number of spikes, you're at risk of that tie plate coming loose, and you're at risk of a derailment ultimately. So whether you want to find where there are missing spikes or missing fasteners because you're trying to figure out where your safety issues are, or you're maybe trying to guide a spiking crew and you want to tell them how many spikes they need to replace, this is a way of doing that. So the coordinates, the X, Y, and Z coordinates of all these spikes are automatically detected and reported by the software. Here's another example. We look at the 3D shape of the rail surface, and we're detecting very, very small flaws in the surface, a few millimeters deep, 10, maybe 20 millimeters long, 5 millimeters wide. Another railroad example, so this is an algorithm that's going through and automatically detecting missing fasteners. This is a type of fastener called a fast clip, and it's on a concrete tie. And if they have a missing fastener like this, depending on the type of trains that are passing over top of it, they may need to shut down this track immediately. Wooden tie inspection, that's another application. So this algorithm goes through and it finds ties that not only have 1 or 2 cracks, but have sufficient cracks to compromise the structural integrity of the tie. So if you look at the second tie down from the top, or the second sleeper down from the top, there's a crack that's highlighted in red, and that crack goes all the way underneath the rail that's on the right-hand side, and you can see it out at the right-hand side of the image. That's a dangerous condition. And then in this case, the green ties are ties that pass the criteria, they're acceptable. So that's a few examples of the types of algorithms. Many, many more algorithms exist for this technology, and the real strength of a company like Pavemetrics is really all we do is we develop algorithms. That's really our focus. So pretty much anything that you see in the 3D scans or you see in the intensity images can be detected or can be measured. So really it's up to your imagination as to what algorithms might be developed. So conclusion. LiDAR is a great technology. As I said before, it's really well suited to environments where you need a very broad scan. You want to scan a large area. 200 to 400,000 points per second is fine. Plus or minus 5 millimeters is enough accuracy. It's a great technology in those cases. There are some cases where it's not a good technology. If millimeters are important to you, if you need a really, really high resolution scan to be able to do things like rating the condition of the road or finding flaws in railway environments or tunnel walls, LiDAR is not going to be a great technology in that case. So it's not about picking the right technology. LiDAR isn't, less good or less capable of a technology than laser triangulation, and vice versa. It's about picking the right technology for the right job. And so I hope that today you learned a little bit about why you might want to think about laser triangulation, how it differs from something like LiDAR, and maybe gives you some ideas about where you might be able to use that in the future. And with that, I'll pass it back to Sonal.
Thanks, Richard, for the presentation. There are a couple of questions.
Okay.
One question says, you in your presentation you have shown you have presence in India. So where is your office in India?
We don't actually have an office in India, but we do have end users in India. For example, the CRRI, the Central Road Research Institute, has our sensor technology, and they use it to scan highways. And the Tamil Nadu Research Institute also has their technology, and they also use it to scan the condition of highways.
Okay. There is one question. It says, do you have done any work in India?
We haven't done any directly because our business model is not to provide services. We simply supply the hardware to other people that then provide those services to the end user. We haven't done any direct work in that regard in India, but we do have a number of customers that have done direct work in India.
Okay, there's one question. It says LiDAR is a great technology, as you say. How do you see it for India if we talk about smart cities?
Yeah, I think that's a good question. I think that there's probably room for both the use of LiDAR and 3D triangulation in a smart city type scenario. One of the things that's important about a smart city is getting that base map of sort of in broad strokes mapping the environment. And LiDAR is a really great technology for doing that. But then the next phase of, okay, I have my broad strokes sketch of the environment. Now I need to make intelligent decisions about how best to manage those assets in my smart city. That's where something like laser triangulation is going to give you the ability to get the resolution that you need, the accuracy that you need, and to process the data in an efficient manner as well.
Okay, Richard. The last question says, what kind of accuracy we can get from using LiDAR technology or 3D triangulation?
Yeah, so LiDAR, you're typically going to see plus or minus 5 millimeters per point. That's a high-end LiDAR system. I always try to quote as high a LiDAR system as I can for a presentation like this, because it's not fair to sort of pick the least capable LiDAR system and then compare it to something like laser triangulation. So a high-end system, LiDAR, you should expect to get plus or minus 5 millimeters per point. If people know what they're doing and they're operating the equipment well, that's pretty normal. With laser triangulation, you should expect to get plus or minus half a millimeter per point from a Z perspective, and you're going to be in the 1 millimeter range from an X and Y perspective. So yeah, it's pretty high accuracy.
Okay. Thanks, Richard, and thank you all the participants for joining us today. We'll have the recording of this webinar placed in our webinar archive for reference and viewing at later date. Thank you all for joining today. Keep you posted on our further activities on our web portal. Thanks, Richard.
Okay, thank you, Sonal. Have a good day, everyone.